The Tacoma Narrows Bridge did not need a once-in-a-century storm to destroy it. It needed ordinary wind, a very slender deck, an emotion the design process had not learned to fear. For months, the bridge moved and survived, so the movement became part of its personality. Then, on November 7th, 1940, the motion changed. The deck began twisting. The air fed the twist. The twist fed the air. The bridge was not just hit by the wind. It became a machine for turning wind into its own failure. To understand how that machine got built, start with a design that was not built. The original proposal for a bridge across the Narrows came from Clark Eldridge, lead engineer for the Washington State Highway Department. His design was conservative by the standards of the day. A two-lane suspension bridge with deep, open stiffening trusses 25 feet deep along the deck. That design was not the one that got built. When Washington sought federal funding, the Public Works Administration required outside consultants. Leon Moissaieff, one of the most prominent suspension bridge engineers in the United States, redesigned the superstructure. He had helped shape the theory behind some of the country's great suspension bridges. He was respected and accomplished. He also told the PWA his revisions would cut the estimated cost from roughly $11 million to $7 million. The critical change was the deck. Instead of Eldridge's deep open trusses, Moissaieff used solid plate girders just 8 feet deep. Where Eldridge's deck would have let much more air pass through, Moissaieff's presented a broader solid surface to the wind. The bridge was also extraordinarily slender. Its center span was 2,800 feet long, while the deck was only 39 feet wide between the cables, a ratio of 1 to 72. For bridge designers of the 1930s, that kind of lightness and grace looked like the future. The redesign was approved. Construction began in November 1938. The bridge opened to traffic on July 1st, 1940. Almost immediately, it moved. Drivers and pedestrians noticed the vertical undulation first. The deck rose and fell in long waves. The motion was so conspicuous that the bridge quickly acquired a nickname, Galloping. Engineers knew about the movement. Before the collapse, the state had already hired University of Washington engineer F.B. Farquharson to study the oscillations and recommend remedies. Tie-down cables had been installed on the side spans. Wind deflectors were under active consideration. The movement was not treated as an immediate emergency. It was treated as an alarming peculiarity, but still a manageable one. People drove across the bridge for the experience. Each day the bridge moved and remained standing, made the motion easier to categorize as a property of the bridge, rather than evidence of a failure already in progress. That matters. Visible anomaly had been normalized before the catastrophic mode ever arrived. On the morning of November 7th, the bridge's behavior changed. The familiar vertical motion gave way to torsional motion. Shortly after 10 a.m., the deck began twisting. By 11:10 a.m., the center span had fallen. What followed was not the wind simply overpowering the structure. It was a flexible structure interacting with wind in a way the design framework of the time did not know how to evaluate well. To understand why, you have to look at 5 conditions that were in place before the first cable was spun. First, the redesign prioritized slenderness, economy, and visual grace. Moissaieff's work grew out of deflection theory, an advanced framework for suspension bridges. In that framework, the dead weight of the bridge, the cable system, and the stiffness already built into the structure could do far more of the stabilizing work than older practice had assumed. The payoff was real. Bridges could be longer, lighter, cheaper, and in the eyes of many engineers, more beautiful. For the loads that theory modeled well, it was powerful. Tacoma Narrows was not built by ignoring engineering. It was built by applying advanced engineering within the limits of what that engineering had formalized. Second, bridge design theory still treated wind mainly as a static load, not a dynamic conversation between air and structure. In the 1930s, suspension bridge engineers were highly capable at analyzing gravity loads, traffic loads, and steady horizontal wind pressure. What they did not yet have was a mature, standardized framework for aerodynamic behavior in very flexible, long-span bridges. Wind was generally treated as a force that pushed on the structure, not as something that changed when the structure itself began to move. That distinction is everything. If a bridge moves in wind, it changes the airflow around its deck. The changed airflow alters the force on the deck. That altered force changes the next motion. The bridge is no longer just resisting wind. It is helping create the conditions of its own next displacement. Dynamic wind tunnel testing existed in aeronautics. It was not yet a routine requirement in suspension bridge design. Third, the bridge's motion had already been absorbed into the category of spectacle. Between July and November 1940, the bridge's oscillations were visible, documented, and widely discussed. Farquharson was studying them. Remedies were being developed, but traffic continued. The nickname stuck, and the bridge's motion became part of its identity in public life. When a system produces conspicuous abnormal behavior and survives, people begin to discount the warning. The bridge taught its observers that movement could be dramatic without being fatal. That lesson held until it didn't. Fourth, the design had not been subjected to the kind of aerodynamic testing that later became standard. This was the clearest gap. The problem was not that the calculations were sloppy. The problem was that the design process of 1940 did not yet routinely demand a dynamic aerodynamic investigation of a bridge deck like this one. After the collapse, the Federal Investigating Board identified excessive flexibility, the aerodynamic effect of the solid plate girder deck, and the need for wind tunnel model testing as central lessons. Those lessons were learned after the bridge fell, not before it was built. Fifth, once the bridge entered large torsional motion, the motion itself began feeding the forces acting on it. Engineers still debate some details of the transition from vertical oscillation to catastrophic twisting, but the standard modern explanation centers on self-excited torsional flutter, a self-reinforcing twisting instability. In that kind of instability, the twisting of the deck changes the airflow in a way that adds energy back into the twist. The motion becomes self-reinforcing. The wind did not need to become a hurricane. It only needed to keep supplying the flow field that the moving bridge was already turning into fuel. This is why Tacoma Narrows is so often misunderstood. The famous footage tempts people to call it a simple resonance story, as if the wind just happened to hit one magic frequency and the bridge obediently shook itself apart. That is too simple. The stronger account is an aerodynamic one. Vertical motion, vortex effects, torsional instability, and a bridge deck so flexible that once the twisting mode took hold, the airflow and the structure began driving each other. The bridge did not merely fail in the wind. It became aerodynamically unstable in the wind. The collapse had an immediate effect on the profession, even if the exact mechanism was not settled in a single afternoon. Investigations began at once. The Federal Board reported in March 1941. University of Washington wind tunnel work continued through the 1940s. The Advisory Board on the Investigation of Suspension Bridges met from 1942 to 1954. Engineers re-evaluated other long-span suspension bridges and began designing later spans with far greater attention to aerodynamic stability. The replacement Tacoma Narrows Bridge, opened in 1950, looked much more like Eldridge's original instinct than Moisseiff's 1940 deck. It used a much deeper, open stiffening truss, features to let air pass through the deck, and additional damping devices. That was not an aesthetic correction. It was a new engineering answer to a newly formalized problem. The collapse did not reveal engineering negligence in the simple, moralized sense. Moisseff was not guessing. He was applying the best accepted theory available to him, and that theory had worked impressively within its domain. What the collapse revealed was that the domain itself had an edge. Past that edge, the equations were not wrong. They were incomplete. The deeper failure was not that the bridge was slender, or beautiful, or inexpensive. It was that the design tools used to judge the bridge were optimized for loads they had been built to handle, while aerodynamic instability in flexible bridge decks had not yet been fully absorbed into ordinary bridge practice. The bridge was not dynamically vetted against that problem in the way later generations would consider essential. This kind of failure recurs across the history of engineering. It is not the failure of knowingly ignoring a risk. It is the failure of working inside a framework that has not yet formalized a real risk, even when clues to that risk are already present. In aviation, aerodynamic behavior was already central. In suspension bridge design, it had not yet crossed fully into routine design practice. The knowledge was nearby. The discipline boundary was real. After November 7th, 1940, that boundary did not survive intact. The field changed because it had to. Wind tunnel testing became commonplace. Aerodynamic stability became a standard concern in long-span bridge design. Designers paid much closer attention to deck shape, torsional stiffness, damping, and the way moving structures feed energy back into the air around them. That is how engineering learns, not cleanly, not abstractly, often by discovering, in the wreckage of a real structure, the exact point where a trusted model stopped matching the world. The Tacoma Narrows Bridge twisted for a little over an hour before it fell. Cameras were running, engineers were watching. By then, the bridge was already doing something its designers had never been required to prove it could survive. Everything needed for the failure was present long before November 7th. The shallow plate girder deck, the extraordinary slenderness, the weak torsional resistance, the absence of dynamic aerodynamic testing, and a profession that had not yet made those questions routine. The wind that morning did not create the design weakness. It revealed it. What failed at Tacoma Narrows was a bridge. What else failed was the boundary of a model. The failure was real. The cause chain was longer. Next time, another design failure. Another system that taught itself to ignore what it had not yet learned how to name.
Specificity and rank define the order, but fragile architecture can't hold water. It's a cascade of forgotten code. A heavy legacy begins to overload. A cascade of effects.